The nice thing about the hydroboration-oxidation reaction of alkynes is it's just like the hydroboration-oxidation reaction of alkenes. In fact, the oxidation part of it is exactly the same series of steps. It really doesn't matter. The boron doesn't care if it's attached to a pi bond or not. And it's still a one-step concerted mechanism for the initial step. Right. The boron in this case has just one hydrogen attached to it and two alkyl groups. These two alkyl groups will actually get oxidized off, and we'll get 2 moles of cyclohexanol at the end of the oxidation step. So there's a reason why we have these two alkyl groups. There's 2 reasons actually. One is we only have one hydrogen that can be donated, which means that it's now a 1-to-1 ratio between the alkyne and the boron. And the other thing is these really sterically hindered bulky groups on there prevent a second addition, right? We don't want the pi bond of the intermediate to add a second boron. We want one boron only. So we're going to go for the transition state here where, just as before, we have one of those pi bonds breaking. We have a bond forming to the hydrogen, a bond breaking between the boron and the hydrogen. Partial positive built up on that carbon, partial negative charge built up on the boron. And when we're done, we're going to have the boron attached, the electrophile, which is the boron. Right? The nucleophile is the hydride, that goes to the more substituted end. The electrophile is the boron. Because it's always the case in every one of these reactions, whether it's Markovnikov or anti-Markovnikov, that the electrophile ends up at the more substituted end, and the nucleophile ends up, the electrophile ends up at the less substituted end, and the nucleophile ends up at the more substituted end. Right? So we've done the hydroboration. Right? And this is now too hindered to add a second boron to the pi bond. And it doesn't have any more hydrides on it, so it can't add to another alkyne to generate a dialkyl material. So the hydroboration step is one step again, concerted mechanism. And to make it simpler for the oxidation, we'll just write R. This was a syn addition, right? Doesn't really matter that it's a syn addition, but it is a syn addition. The boron and the hydrogen are added to the same side of the triple bond. So now we do the oxidation. So what was the first step of the oxidation last time? Because it's the same reagents, it's hydrogen peroxide and base. And if you remember what the first step of the oxidation was last time, it's going to be the same first step of the oxidation this time. How many people are still here?
An acid-base reaction.
Just an acid-base reaction of 10 to the third for the more acidic hydrogen peroxide being deprotonated by the OH group to generate water, and that equilibrium constant is about 10 to the third again, which means I really ought to be writing this arrow very long. Right. So what was the second step? Right, this is just the acid-base reaction. What was step 2?
Nucleophilic attack on boron.
Hydrogen peroxide ion attacking boron. So you get 2 for 1 here. If you know the mechanism for the oxymercuration, demercuration, the hydroboration oxidation of alkenes, you also know the mechanism for the oxidation. So step 2, right, nucleophilic attack on boron. Because boron has the unfilled octet. Now it's unhappy because it has a negative charge. So what's step 3?
Alkyl shift.
And that's the key step, right? That's a tilde R, where this alkyl group pushes out hydroxide to take the negative charge off the boron and generate a carbon-oxygen bond and hydroxide ion. So now boron's unhappy again for a different reason. Now boron's unhappy because it has an unfilled octet. So step 4. You're on a roll.
Hydroxide ion attacks boron.
Yep, another nucleophilic attack on boron, making boron unhappy because it has a negative formal charge. Sulfy bond. And then step 5.
It attacks the boric acid. Boric acid.
Not yet. We haven't lost the alkoxide yet. You skipped to step 6.
Sorry. You'd lose the alkoxide and then it would deprotonate the boric acid.
Yep. So the catch is, right, this alkoxide ion could deprotonate that, but that's resonance stabilized. You've actually got a resonance structure that has a negative charge on the carbon instead, and the aldehyde functional group. And it's more stable to have the carbon-oxygen double bond than it is to have the carbon-carbon double bond. So we're actually going to protonate that at carbon rather than at oxygen. And that's what's going to generate the CH2 group and the aldehyde. And so the proton transfer protonates at carbon. This is the less stable resonance structure, but it's the one that reacts. If you didn't know that, right, if you just took that intermediate that had the negative charge on the oxygen and protonated it, you would generate an enol. So step 6, generate the enol. But the enol is not stable, and it's no more stable in base than it is in acid. So that keto-enol tautomerism reaction can occur in base just as it does in acid. You take that proton right back off, to generate the alkoxide ion, which is actually called an enolate ion. And then water would protonate the carbon to generate the aldehyde. So that's the keto-enol tautomerism reaction. It's 2 steps in base just as it is in acid. But the steps are reversed, where the first step is to deprotonate the oxygen and the second step is to protonate the carbon. It doesn't really make sense to generate the enol and then just ungenerate it again to form the alkoxide. It makes a lot more sense just to make step 6 of the oxidation, protonating at the carbon from the less stable resonance structure. That's it, right on time, 10:09. Right, so the oxidation step is pretty much the same. The oxidation reaction is pretty much the same series of steps for the alkyne as it is for the alkene.